the next thing we're going to do is see how we can use calculus to sketch the graph of really any function. And we're going to see that the basis for the results we're going to use is the mean value theorem. So first, we're going to look at three corollaries of the mean value theorem. A corollary is a small, quick result given a larger theorem. So it's like an immediate consequence of a larger theorem. And we have three corollaries here. I'll give a proof for the first one, I guess. Oh yeah, I'll give a proof for the first one. Corollaries. First, let f be differentiable on a to b. Open. If f prime equals 0 on a to b, then f is constant. So if the derivative, well, before we had the result that if f was a constant function, then its derivative was 0. Here, we're going in the other direction. We're assuming that the derivative is 0 on an interval, and we're able to conclude that f is constant on that interval. So I'll give a proof of that right here, I guess. Proof of 1. Yeah, I wasn't going to, but let's do one proof. We want to conclude f is a constant. Well, consider the interval. Well, let's just consider, what's our notation for that? Let's just say x, y, inside a to b. So here we're taking a closed interval inside a to b. So we have a to b somewhere on our x-axis, x to y is somewhere inside that. Well, what can we conclude using the mean value theorem? Well, then, by mean value theorem, MVT, there is some c inside x to y with f prime of c equal to what? F of y minus f of x all over y minus x by mean value theorem. But our assumption is that inside this interval a to b, f prime is always 0. C is within x to y, so in particular it's within a to b. So by that assumption over there, that equals 0. Well, what happens if that is equal to 0? Well, 0 equals this, multiply by the denominator, you get, so 0 equals f of y minus f of x. I would write this under there, but there's no room, so I'm going to write it over here. Then f of x equals f of y. So any x and y inside a to b satisfy that f of x equals f of y. In particular, the y values inside a to b are the same height. So the function is constant. So there's a proof of 1. There are proofs of 2 and 3 in the textbook. You can look at them if you want. This proof may differ from the textbook. I didn't consult it. So we have that. If f prime is 0, then f is constant. We're going to use that result in Chapter 5 the week after our next exam. Number 2, let f and g, two functions, be differentiable on open a to b, and assume f prime equals g prime on that interval. So the derivatives are the same. Two functions have the same derivative. Then they equal each other up to a constant for some constant c. So f of x equals g of x plus some constant c. C could be negative. So here, if we have two functions where the derivatives are the same, then they are the same function up to a constant, meaning they differ by a constant. We're going to see that also in Chapter 5. But here, for what we're going to do with graphing, number 3 will be very important. 3. If f is continuous on a to b, differential on a to b, open, then a. If f prime is greater than 0 on a to b, so f prime is positive on a to b, then f is increasing on a to b. Similarly, part b, if f prime is negative, then f is decreasing. Now, we technically haven't defined increasing or decreasing. They are exactly what you would expect. Increasing if the function is going upward, decreasing if it's going downward as x gets larger. The technical definition of increasing and decreasing is, I think, far more tedious than just visualizing a function going up or a function going down. But let's use this result in this example. So here we have a graph of the derivative. So this is not a graph of f of x. This is a graph of f prime of x. Given the graph of the derivative, find intervals on which f of x is increasing or decreasing. Now, if it said find intervals on which f prime is increasing or decreasing, well, then you'd say negative infinity to whatever that x value is. It's increasing because it's going up, f prime, decreasing on the other interval. But here, we have a graph of f prime, and we want to know where f is increasing or decreasing. Well, we use this last result. If f prime is positive, then f is increasing. Where is f prime positive? So I'll just say f is, I guess I used of x in the question, f of x is increasing it's increasing where the derivative is positive. Here's f prime of x. It's positive from -1 to 4. And that's the only spot where it's positive. The second part says if f prime is negative, then f is decreasing. Where's f prime negative? Well, it's negative over here, and it's negative over here. So f is decreasing on, what do we have? Negative infinity to -1 and 4 to infinity. So we needed where f prime was positive, where f prime was negative, and that allowed us to conclude information about where the original function f is increasing, where it's decreasing. And we're going to see more on that in a moment. But to this point, maybe I should call this a remark. Remark. To this point, we can't use calculus to differentiate between a local maximum and a local minimum. Misspelled. Calculus. To differentiate between a local maximum and a local minimum. Why can't we? Well, remember, a local maximum could look something like this. A local minimum could look something like this. All we know is a local maximum will occur where the derivative is 0 or where it's undefined by our extreme value theorem lecture discussion. But we can't say we can't answer yet what is the difference between these 2 points using calculus. But now that we have this third corollary of the mean value theorem, we can differentiate between these two using calculus. We can observe that to the left of this local maximum, this function is increasing. To the right, it's decreasing. And similarly, for a local minimum, it's decreasing and then increasing. And we can record this as another theorem, which we call the first derivative test. The first derivative test. Let x be a critical point for f of x. Now remember, a critical point, let's just say for f. I don't use f of x anywhere else. Let x be a critical point for f. So a critical point remember, is where the derivative is 0 or where it's undefined. 3 parts. 1. If f prime is positive to the left of x and f prime is negative to the right of x, then f has a local maximum at x. Part 2, if f prime is negative to the left of x and f prime is positive to the right of x, so flipping part 1 around, then f has a local minimum at x. Part 3, if f prime has the same sign on each side of x, then f does not have a local maximum or a local minimum at x. Now let's just look at a couple graphs illustrating each of these 3 cases. So, example, we illustrate the 3 cases in the previous theorem. 1, well, we have local maximum. We have f prime is positive to the left, f prime is negative to the right. What would that look like? Well, remember, with our third corollary of the mean value theorem, if f prime is positive, then the function is increasing. So it's increasing until it gets to x, and then it starts decreasing. Let's draw a little better. I need a new marker. So increasing to the left of x, decreasing to the right, what would that look like, or what could that look like? Could look like this. X is right there. X would correspond to that peak. F prime is positive to the left, f prime is negative to the right. Why is f prime positive to the left? Well, the function is increasing. Over here, to the right, the function is decreasing. And the function does have a local maximum at x. In this case, an absolute, but in particular, a local. So there's case 1. What would case 2 look like? Well, we can just flip it around. Or you can turn your laptop upside down if you want. Or computer. I can't easily put these boards upside down. Well, I could by removing a couple of these screws and flipping the board around. But it's easier to just draw this. As you saw, it took only a second. So here, for this x value, f prime is negative to the left of x, it's decreasing to the left of x, and increasing on the right of x, and it does, this function, have a local minimum at x. Now, for case 3, if f prime has the same sign on each side of x, well, technically that's 2 cases to consider, positive sign or negative on each side. Well, I'll just draw one of them. The other is just, flip it around. Then f does not have a local maximum or a local minimum. What would that look like? Well, f prime has the same sign on each side of x, but x is still a critical point. The derivative is still 0 at x. What could that look like? Well, it could look something like this, where we're increasing until we get to x. We flatten out to give us our horizontal tangent for a critical point, but then it continues to increase afterwards. So right here, for that x value and this function, f prime is positive on both sides of x. The derivative at x is 0. And you can see this does not have a local maximum or a local minimum. Another example, or consider f of x equals x cubed at x equals 0. X cubed demonstrates the same thing, where it's always increasing, but 0 is a critical point because 3x squared equals 0 and x equals 0. And also, if you wanted, right here the derivative is positive everywhere. If you want a negative, you could just flip that around. So we have a couple graphs that we are interpreting using increasing, decreasing, but can we see a little bit more. Well, we can see a little bit more if we think purely about the derivative. So our third corollary of the mean value theorem said if f prime is positive, then it's increasing, and so on. I didn't really talk too much about why that is, but we can see on these graphs why that is using our tangent lines. So in this case, in case 1, f prime is positive to the left, f prime is negative to the right, increasing on the left, decreasing on the right. Well, we can see that on the left of x, our tangent lines are all positive. Tangent lines are positive, and the function is increasing. Tangent lines, tangent meaning the slopes of the tangent lines are positive. Slopes of tangent lines are positive, and it's increasing. Until we get to the top of that, then it flattens out. So we can see, just using our tangent lines and letting them travel on the curve, what an increasing function could look like using the derivative. And similarly, well, what a function which is increasing on an interval looks like using the derivative. Similarly, on the other side, the right side of x, we can see that our tangent lines have negative slope, derivative is negative, and the function is going down. In this case, it's getting more negative. More on that in a moment. But just by using our tangent lines and letting them travel, we can see how we can conclude the function is increasing, is increasing or decreasing just using the derivative. And similarly for this one, it's decreasing with negative tangent lines over here, increasing with positive tangent lines over there. And in this third one, notice all of our tangent lines have positive slope, except for that one where it's 0. As you travel on this curve, we have only positive slopes, so the derivative is always positive, and the function is always increasing. So we've discussed in a good amount of detail how we could apply the mean value theorem to the first derivative, and we got a lot of information from that. Well, we can do the same thing with the second derivative, because the second derivative is just the derivative of the derivative. So let's remember exactly what we're doing with the derivative, or what we are seeing with the derivative. Recall, a derivative measures a rate of change. So this notation, dy dx, one of the reasons it's convenient is because when we see that, we could think of how y is changing as x is changing. dy dx tells us how y is changing as x is changing at an instant. But the mean value theorem allows us to sort of understand that in intervals as well. But the first derivative tells us how the y values are changing as the x values are changing, and we understand that as the slope at a point. But in particular, we understand that as the slope. But what if we apply that same reasoning to the second derivative? Well, the second derivative is the derivative of the derivative. A derivative measures a rate of change. The first derivative measures a rate of change of a function, of a y value, given x values. Here, we're looking at the second derivative. The derivative of the derivative tells us how the derivative is changing as x is changing. In particular, the derivative of the derivative tells us how the slope is changing. So we're going to look at these two examples. So I have 4 things labeled f. That's for convenience for what I'm about to write down here. But in these examples, these two types of graphs are going to go together. And these two types of graphs are going to go together, and we'll see more on that in a moment. But for now, let's try looking at how the derivative is changing by considering how slopes of tangent lines are changing. Now let's start here. How do slopes of tangent lines change as x gets larger? Well, we have these with positive slope over here. But let's let x get larger. What happens to the slopes of our tangent lines? Well, look at that. The slopes are getting larger. They start here at a positive number, a relatively small positive number, and then they get larger. Start as a small number and get larger. The slope is getting larger. the derivative is increasing. Slopes of tangent lines start here and get larger. How about in this next one? Well, right here, we have this slope. It's negative, this slope of the tangent line. But what happens as x gets larger? So we have a negative slope, and we're letting x get larger. Negative slope, well, it's still negative, but it's getting less negative. The slope of the tangent line starts as negative and gets less negative. The slope of the tangent lines in this second case is also going up because it starts very negative and it's getting less negative. Here in the first one, we started a positive and get more positive. The slopes of the tangent line are getting larger. Here, we start at a very negative slope and they get less negative. Well, in each case, the slopes of the tangent lines are getting larger. So in these graphs, as x gets larger, the slopes of the tangent lines become larger. So one is starting as a small positive, getting more positive. One is starting as a large negative, getting less negative. In either case, in each case, the slopes of the tangent lines become larger. In particular, that tells us if the slopes are getting larger, well, the derivative tells us about the slopes. Here, slopes are getting larger, the derivative is going up. Derivative is increasing. In particular, that's a lousy prime. Too diagonal. In particular, f prime, that's not much better, is increasing. Because the slopes of the tangent lines are getting larger. Well, let's look at these next two. You may be able to fill in both of these sentences without even looking at these graphs. So we have this first example with these two curves, and we'll see more on them. And what about these next two? Well, again, we're going to do the same analysis. Slopes of the tangent lines here start as a positive, and they still are positive as x gets larger, but they start as a large positive and become a smaller positive. So they start as a large positive and become less positive. Slopes of the tangent lines are going down as x gets larger. And over here, they start as a small negative and they get more negative, slopes of the tangent lines. They start as a small negative and they get more negative. Here, the slopes of the tangent lines are also getting smaller. So in these graphs, as x gets larger, the slopes of the tangent lines become smaller. In the first, they start as a large positive, get less positive. In the second, they start as a small negative and get more negative. In particular, f prime is decreasing. Now remember, our goal here is to understand how we can apply, well, how we can get a corresponding first derivative test for the second derivative. And here, this is building up to that because right here, notice we have f prime. We're looking at how f prime is changing. And the second derivative tells us about how f prime is changing. But before we get to our second derivative test, let's just define a couple words. Definition, and these two examples are going to be the splitting of the two cases of this definition. Definition, let f be differentiable on A to B open. If f prime is increasing, then f is concave up. So if f prime is increasing, then f is concave up on the interval. Similarly, if f prime is decreasing, then f is concave down on the interval. Now, what does that mean? Well, what does that look like, I should say? Well, if we go back to these two examples, in this one, note the last sentence, f prime is increasing. Well, that would correspond to case 1. So in this case, these functions should both be concave up, and they are both concave up by that definition. And why are they concave up? Well, they're concave up because f prime is increasing. or f prime is increasing because the slopes are becoming larger, but we can actually see that in this graph if we look at the caved-in portion of this. So we call it concave up, concave down, because to understand concave up, concave down, we don't necessarily have to get into the details of the first derivative, the second derivative, slopes of tangent lines, and so on. We can just look at these curves and look at their caved-in portion and look at where the caved-in portion is pointing. And I commonly will draw an arrow going away from the caved-in portion like that, because I think it makes it even more clear. In those first two, the caved-in portion is pointing in the upward direction. In these next two, the caved-in portion is pointing in the downward direction. But now, we have all these observations. Let's now apply corollary 3 of the mean value theorem to the first derivative. So to get the first derivative test, we applied corollary 3 of the mean value theorem to a function. Here, we're going to apply it to the first derivative, which will give us results on the second derivative, and we'll call that the second derivative test. Theorem, the second derivative test. Let f be differentiable on a to b open. Two parts. One, if the second derivative, f prime prime, is positive on a to b, well then by corollary 3 of the mean value theorem, then f prime is increasing. And by this definition that's erased, we conclude if f prime is increasing, then f is concave up. So jumping over corollary 3 and jumping straight to the definition, if f double prime is positive, then f is concave up. 2, if f double prime is negative, then f is concave down on a to b. So corollary 3 of the mean value theorem combined with our second derivative test tells us that the first and second derivatives tell us a lot about the behavior of a graph, just by looking at where the first and second derivatives are positive and where they're negative. And I'm going to consolidate that information in 4 graphs in a moment, but before we get there, we just need a quick definition. So with the first derivative, we saw that where the first derivative changed from positive to negative, we had a local maximum, or a local minimum for the other case. I may have said that backwards. But here also, when the second derivative changes, we're going to have another visual that shows up a couple times. So we'll just define that here. Definition, if f is continuous at x and changes concavity at x, then we say f has an inflection point at x. And let's just illustrate that with actually 2 examples. One, well, let's just illustrate it here. I'll illustrate it here so I can use an entire board. Example illustrating this. Here, f has an inflection point at x let's make it look like this. Here's f. Why does it have an inflection point at x? Since f is concave down, abbreviate, concave is a large word, so, and down is also a large word, so we can abbreviate concave down, just CC with a downward arrow. It's concave down on negative infinity to x, and concave up, also abbreviating those concave, CC, up, arrow up, on x to infinity. Why is it concave down? Over there, well, we can see it's concave down by looking at the caved-in portion that's pointing down. Here, the caved-in portion is pointing up. So here, f has an inflection point at x. Now, why do we need that assumption that it's continuous in order to define that? We illustrate y, assuming continuity, is necessary. So why is that necessary? Well, if we take 1 over x. That's a pretty good 1 over x. Well, you take 1 over x, well, look at the caved-in portions. Concave down, concave up. Here, f is concave up and down. Here, f is concave down on negative infinity up to but not including 0, and concave up on 0 to infinity. But we wouldn't want to say that it has an inflection point at 0. But there is no inflection point at x equals 0. The function is not defined at x equals 0. So, you know, if it's continuous and changes concavity, we will have a point like that, that looks like that. But if it's not continuous and changes concavity, which could happen, then we're not going to want to call that an inflection point. But let's summarize all of the information we've covered so far in 4 nice graphs. Remark. A sketch of the graph of f of x can be found by identifying intervals over which f of x looks like one of those 4 graphs and piecing together the result. Now, under each of these, I am going to write 4 things for each graph. But we can use the first and second derivatives to analyze these 4 graphs. How can we do that? Well, right here, notice I call them all f. That's okay. Notice the function is going up. So I'll just say f increasing. Here, f is also going up. Notice it's going up less quickly, but it's still going up. What does that mean, less quickly? I'm going to write this a little higher since I don't have that much space. F. Now what am I writing? F increasing. What about the third one? Well, this one's going down, so here f is decreasing. And here, this one is also going down much faster. What does that mean? And this function is decreasing, this last one. Now, we can tell more about this by looking at the concavity. Here, f is concave up. Here, f is concave down. So notice the concavity in this case is going to differentiate between, well, it'll allow us to differentiate between whether something is increasing quickly versus slowly. You know, that's really what concavity is measuring. You know, it has this convenient caved-in portion interpretation, but it is measuring how fast something is increasing or decreasing. Here, the caved-in portion is going up. Here, the caved-in portion is going down. I could say is between these, but who wants to write is, 8 times? Yeah, even in my notes I didn't write is. So we have all this information. So we need to figure out, to sketch a graph, we need to figure out increasing, decreasing, and concave up, concave down. But we have lots of derivative results which allow us to reach those conclusions. To determine if a function is increasing, well, we just need to find where f prime is positive. So increasing has f prime positive. Decreasing has f prime negative. And similarly, for concavity, our second derivative test told us that when a second derivative was positive, it's concave. That prime is a little far away. Prime. The second derivative tells us that when the second derivative test tells us that when the second derivative is positive, the function is concave up. So here we have first derivative positive, second derivative positive. Here we have first derivative positive, second derivative negative. Here, first derivative negative, second derivative positive, and here, first derivative negative, second derivative negative. So if we want to find the sketch of a curve, well, all we need to do is find the intervals over which the function looks like one of these four, and we can do that by looking at the signs of the first and second derivatives. And then, all we have to do is piece together the result. So let's do that. Well, before doing actual functions, let's look at one other type of example. Just using this. I shouldn't have erased the one I just erased. Yeah, I guess that's fine. I'll just adjust the example. Example. Sketch a graph I forget the example. Did I want increasing or always concave up? I wanted, okay, sketch a graph which is, sketch a graph with f prime always negative and f prime prime positive on, which one do I want? F prime always negative, f prime prime positive on 3 to infinity, f prime prime negative on negative infinity to 3. So how can we do this? Well, we need f prime always negative. So that tells us immediately the function is always going to look like one of those two. Well, either of those two. But we need f prime prime positive, second derivative positive, on 3 to infinity. So we need the function to look like this on 3 to infinity, but we need it to look like this on negative infinity to 3. So what could that look like? Well, let's mark off 3. Let's put one of those on, let's start at negative infinity. Let's put one of these on negative infinity to 3. Well, there's one of those. And then let's put one of these on 3 to infinity. I screwed that up with that last thing, trying to make the line darker. So we put one of those on negative infinity to 3, and we put one of these on 3 to infinity. And here, you can see concavity does change at 3, and you can see that the function is always decreasing. But we got that by looking at our 4 graphs, looking at the signs of the derivative, and then just taking the pieces we need. So let's do that with a couple more functions. Sketch a graph of these 3 functions. F of x equals x cubed minus 6x squared plus 9x plus 30. Part B, f of x equals 2 plus 3x squared minus x cubed. C, f of x is negative 2x squared plus 5x minus 2. And on these graphs, I just wrote directions to sketch a graph. I could include things like label, local maximum, local minimum, label inflection points, and so on. But we're going to do this by identifying intervals over which the function is one of those 4 graphs. And how are we going to do that? Well, we need where the first and second derivatives are 0, and then we need to interpret that. So in particular, we need first derivative. So f prime for part A is 3x squared minus 12x, good minus sign, minus 12x plus 9. We want to set this equal to 0. Well, let's see, for organization, where am I going to put everything? Okay. So equals, I'm going to factor out a 3 first. 3 and x squared minus 4x plus 3. We want to set this equal to 0, but this does factor nicely. So I'm just going to factor it now. X negative 3, negative 1 make positive 3, negative 3, negative 1 make negative 4. Set that equal to 0. That's 0 when x equals 1 or when x equals 3. Now, we can use these values to, well, these values split the number line at 1 and 3. They split into 3 pieces, so into 3 intervals, and on those intervals, the first derivative will always be positive on each of those on each of those intervals. The first derivative will either always be positive or it will always be negative, and we have to figure out which one. How are we going to do that? Well, I like doing that with a number line. Mark off 1 and 3, and I'm going to write something. Well, first of all, you can see we now have 3 intervals on the real number line, and I'm going to write something above each piece and below each piece. So what does the first derivative tell us? The first derivative, if the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. So we need the sign of the first derivative in each piece. So let's find that. F prime, we just need the sign. We already found where it's 0, which tells us in each piece it's always either positive or always negative. So all we need to do is pick a point in here, pick a point in here, pick a point in here, evaluate the first derivative, and figure out the sign. So here, I'm going to pick 0. 0's in this interval. At 0, the first derivative, well, up here it tells us the first derivative is positive. It's positive 9 at 0, but in particular it's positive. You know, the fact that it's 9 doesn't matter. So I'm just going to say f prime is greater than 0 there. Next piece, we have 1 to 3. We're going to do the same analysis. I'm going to pick the number 2. That's a nice number. We need the first derivative evaluated at 2. Well, that's too many numbers to think of. But conveniently, we have a nice factored form. So I'm just going to use 2 in this factored form, and it doesn't matter what number it is, it just matters the sign. So what is the sign when you put 2 in there? Well, it's positive times negative times positive. Positive times positive is negative. And we'll do the same thing over here. F prime, I'll pick 4. 4 is in that interval. Notice we can't choose 1 or 3, because we've always been talking about open intervals. Why have we been talking only about open intervals? Well, notice here, at 1, the derivative is 0. And we want where it's positive or negative. And similarly, at 3, the derivative is 0. What happens over here at 4? Well, you get positive times positive times positive, which is positive. You could have also done put 0 in the factored form, and you'd get positive times negative, which gives you that positive. Now, why did we do all of this? Well, we did all of this so we could find the intervals on which the function is increasing or decreasing. That's what the first derivative tells us. Well, one of the things it tells us. Where the first derivative is positive, the function is increasing. Where the first derivative is negative, the function is decreasing. So right here, we've done everything we could with the first derivative. We found where the function is increasing and where it's decreasing. Now we have to find where it's concave up and where it's concave down. How do we do that? Well, we do the same thing, but with the second derivative. 6x minus 12. Where is this 0? This is 0. When x equals 2, you could factor out a 6 if you want. 6 times x minus 2. It's 0 when x equals 2, and then we'll do the same argument we'll split our number line at 2. In this case, it just splits into 2 pieces. And we want to look at where the second derivative is positive, where the second derivative is negative. On this side of 2, I'll pick x equals 0. When x equals 0, the second derivative is negative. Over here, we can pick a number like 3. When x equals 3, the second derivative is positive. And the sign of the second derivative tells us about the concavity of the original function. So actually down here, I could have said f is increasing. Maybe I should have. Not too many letters. Yeah, the first derivative tells us information about the original function. It allows us to conclude the original function is increasing and the original function is decreasing. Well, or the original function is decreasing. And I'm really debating if I should say f increasing, f decreasing. I think once we actually do a sketch of the graph, it'll make sense without putting f there. Same thing with concavity. The second derivative is negative, tells us the function is concave down. The second derivative is positive, tells us the original function is concave up. Well, now, this number line and this number line, actually what's under those number lines, tells us all we need to know in order to sketch our function. So where do I want to do that? I probably don't have room on one board, so what I'm going to do is just transfer this number line over here. Like that, and erase this second derivative argument so that I can fit the function on this. Now, how are we going to piece together this function? Well, first, I'm going to draw xy plane. And next, I'm going to label these relevant points. In this case, 1, 2, and 3. 1, 2, and 3. Now, before sketching this function at all, just the calculus is actually not enough to tell us what we want. Why? Well, the calculus could tell us, you know, if we piece together intervals, maybe it looks like this. But the same calculus could be used on a function like that. It'll have the same relevant intervals. So what we need before piecing anything together is to find a point. If we know one point, it's going to fix where this function, well, it's going to fix how high the function is at a point, which will fix where the rest of the curve goes. Are there any convenient, easy points to find? Well, 0 is a nice number. When x equals 0, f of x equals 30. So right here we have the point 0, 30. I'm debating where I want to write the ordered pair. So we find the y-intercept. Let x equals 0, f of x equals 30. So now we piece together the result. And how do we do that? Well, we just look at these two charts until 1. Well, first I look over here, actually. The first relevant interval, negative infinity to 1. What happens on negative infinity to 1? Increasing, concave down. Which one's increasing and concave down? It is the, the second one in those 4, which looks like this. So from negative infinity to 1, we'll put one of those. Great. Quarter of the way there. On 1 to 2. 1 to 2 is the next relevant. Oh, notice I also went through the y-intercept there. On 1 to 2, it's now decreasing, but still concave down. What's decreasing concave down? That is the 4th one in our remark. It looks like that. So we're going to put one of those from 1 to 2. This is a polynomial, so it's continuous. So we'll put one of those from 1 to 2. Now I have the splitting of the board to navigate, but that's okay. 2 to 3. On 2 to 3, the function is decreasing and concave up. Which one's decreasing and concave up? Decreasing, concave up looks like that. So we'll put one of those from 2 to 3. And finally, from 3 to infinity, the function is increasing and concave up, which looks like that, the first one of the 4. So we'll put one of those like that. So we have a nice sketch of this curve. Now this one's particularly nice because it does have all 4 of the pieces in the remark. But we could actually ask a little more. You know, I could just say label the local maximum. Well, there's a local maximum. And you could label it with an ordered pair. I mean, the numbers in this are a little inconvenient. Well, I guess with 1 it's not. It would be, what, 34? So you could label it 134. You could label this local minimum. I think it's actually above the x-axis, but that's fine. Yeah, that's a local minimum. What's the local minimum in the actual ordered pair? It's, that's a large number. 57 and 27 is, what, 94? So it's 40, I guess? No. How did I get 40? 27 and 27, 84. Okay, 84. Yeah, okay, 57 and 27 is not 94. What am I talking about? So it's 80, so it's 30. Oh, okay, it's 30. You know, so this x-axis, you know, this x-axis is at, like, well, not drawn to scale. Don't worry about drawing to scale. Worry about the calculus and the importance of the y-intercept. There's a little more calculus in here, because right here at 2, notice the concavity changes, so we have an inflection point. And of course, you could label that with an ordered pair as well. So let's do the same thing with these other 2. B. Well, again, we need the first derivative. First derivative here is 6x minus 3x squared. We want to set this equal to 0, but again, this factors, so I'll factor it right now. We can factor a 3x. Each thing has a 3x. And we're left with a 2 minus x. And when is this 0? It's 0 when x equals 0 or x equals 2. So we'll break our interval at 0. We'll break our interval at 2. And we need the sign of the first derivative on each piece. Well, over here we have to go into negative numbers. Take negative 1. We have, using the factored form, put negative 1 in. You get 3 times a negative, so negative times a positive. Negative times a positive is negative. Pick a number in here, 0 to 2. I'll pick 1. Put 1 into the derivative, you get positive times positive, which is positive. Pick a number over here, 3. You get positive times negative, which is negative. Where the first derivative is positive, the original is increasing. Where the first derivative is negative, the original is decreasing. And now we do the same thing with the second derivative to determine the intervals of concavity. Here, the second derivative is what? 6 minus 6x. When is that 0? That's 0 when x equals 1. We'll mark off 1, and we'll split our interval at 1. The second derivative in this piece, I'll choose 0. All you need to do is choose, one of those values there. At 0, the second derivative is positive. At 2, second derivative is negative. So the function is concave up. where the first derivative is positive, and it's concave down where the first derivative is negative. And now we just need to piece together our graph. So here our relevant values are 0, 1, and 2. So I'll mark off 0, 1, and 2. 0 is already marked off for us. And again, I'm going to find the y-intercept first. I'm going to move my x-axis, my y-axis over a little. So what do we have? We have 0, put 1 there, and I'll put 2 here. At 0, the function is 2. I'll label that ordered pair in a moment. I guess I'll label it now. 0, 2. So our first relevant interval, negative infinity to 0. The original function is decreasing and concave up. What does that look like? It looks like that, decreasing and concave up. So we'll put one of those on negative infinity to 0. There's one of those. Let's make it go to negative infinity. Well, make the x values go to negative infinity. And then we do the same thing with the other intervals. On 0 to 1, increasing, concave up. What does that look like? Well, it looks like one of these. Increasing and concave up. On 1 to 2, it's increasing and concave down. That looks like one of these. You can move 2 around if you want. And then from 2 to infinity, decreasing, concave down, looks like one of those. So here's our sketch. If we wanted to label the local maximum, local minimum, you could be required to. Here's the local maximum. Here's the local minimum. And an inflection point occurs at 1 because concavity changes. And this one, the numbers are convenient enough that I wouldn't mind asking you to find a few ordered pairs. Especially since I already found 0. At 1, this function is 4, so this inflection point is 1, 4. At 2, the function is 2 plus 12, 14, and 8, and a negative, make a 6. So, you could be asked to label them with an ordered pair. If it doesn't say label them with an ordered pair, then you don't have to label them with an ordered pair. You can just label them. But if it does say label them with an ordered pair, then you do have to find the ordered pair. And finally, let's do part C. Same type of argument, first derivative, second derivative. First derivative here, negative 4x plus 5. When is this 0? It's 0 when x equals, what, 5 quarters? Yes, when x equals 5 quarters. We'll split our interval at 5 quarters. First derivative over here, pick 0. At 0, the first derivative is positive. First derivative over here at, say, 2, negative 8 plus 5 is negative. So here the function is increasing, here the function is decreasing. And we'll do the same thing with our second derivative, but notice here, we actually don't have to do the same thing with the second derivative because the second derivative is negative 4. Negative 4 is always negative. So I'll say which is always negative. That's a lot of words. I could have just written less than 0. But if the function is, if the second derivative is always negative, what does that tell us? Well, it tells us something about concavity. So f is always concave down. And we're going to see what that looks like in this graph. We could actually sketch this graph using completing the square. because it's just going to be x squared shifted, x squared shifted around. But here we're graphing with calculus. Now, you learned another way of graphing parabolas in high school, but it's just not a... It's one of those high school results that they make a big deal about, and everybody knows it going into college, and it's... there are so many other things that you could make a big deal about in a high school math class that you don't, and it's really unfortunate. But where were we? Well, the only relevant point here is 5/4. We'll mark off 5/4. On negative infinity to 5/4, well, we need the y-intercept first. Y-intercept here is negative 2. On negative infinity to 5/4, the function is increasing and concave down. It goes through this point, so it'll look like this. And on 5/4 to infinity, decreasing, concave down. Let's smooth that out a little. Decreasing, concave down, so it looks like that. And here we have a local maximum. You notice, I didn't really mention this in the graphs, but notice we have a local maximum because it goes from increasing to decreasing, and it's continuous there. And similarly for the local minima, they all went from decreasing to increasing. And you can see that in that number line. But here we have a sketch of f for part C. It is a parabola. The vertex is 5/4. What's the formula for that? Negative b over 2a, yeah. We have these three graphs on a test, on an exam. I will ask a polynomial similar to one of these. If it is on the test, odds are it'll be on the test and the final. Definitely on the final. But I will ask a parabola. This type of reasoning does apply to general functions. The same first derivative argument, the same second derivative argument. And I will post a document with some other sketches for you to look at. And I'm not going to ask any, with asymptotes, one like this, with all these asymptotes. But do notice that this function and all of the functions that will be posted are still found by finding pieces on which, finding intervals on which the function looks like each of those four graphs. So do look at that. But as far as exam 2 goes, maybe for the next week or two, I should focus more on things like this, and then sometime between now and the final, take a look at the other graphs that are posted.